for this.
Okay, thank you, Kim, to invite me to give the open ceremony for special talk from Ajara, okay, from Department of Mathematics, University of Ivory, Portuguese, right? So this is the third year student from Data Science Research Center, okay, from Chiang Mai University. For this time, this is a time series course. So this is a, I would say, new knowledge, and I want you to suggest maybe how to design the idea of the research, okay, and suggest them to how to learn and the basic concept about your research. Okay, so before you give the talk, maybe my student will give your base biology and introduction to the abstract now. Okay, let's go.
Okay.
Sometimes you provide about the abstract. Oh, sorry, biology.
Okay, so next, I would like to introduce the short biography of Professor Russell Alpizar-Jara. Russell Alpizar-Jara was educated at the University of Costa Rica and North Carolina State University, where he obtained his Master of Science and Doctor of Philosophy in the Biomathematics graduate program within the Statistics Department. His research focused on model development and estimate methods for sampling animal populations, particularly distant and capture-recapture sampling. He is currently an associate professor in the mathematics department at the University of Évora in Portugal, and served as a board member of Portuguese Statistical Society from 2006 to 2011. He has been a visiting professor at the University of Costa Rica and North Carolina State University, and a visiting scientist at the Patterson Wildlife Research Center in Maryland, USA. He has served as associate editor and referee for international peer-reviewed journals, and is especially interested in linking theory with application toward interdisciplinary research. His current research interests include animal population sampling, population dynamics modeling, statistical ecology, wildlife and fisheries, with recent work focusing on distant sampling methods for mountain ungulates.
Inverse formant of discrete random variable, Russell Alpizar-Jara. Research Center of Mathematics and Applications, Institute for Advanced Study and Research, University of Évora, Portugal. Abstract. We investigate the distributional property of the reciprocal of non-negative discrete random variable, focusing on commonly encountered distribution that include uniform, Poisson binomial, and negative binomial and hypergeometry. We derive and present symbolic expression for the expected value, second moment, and variance of the inverse of discrete random variable x. In case where closed form solutions are not tractable, we provide numerical approximation and asymptotic bound. Graphical analysis illustrates the behavior of inverse moment across parameter range, highlighting their sensitivity to distributional tail weight and support. This study contributes useful analytical insight for various applications, inverse expectation modeling, and sensitivity analysis involving reciprocal of count-based random variable.
Thank you, TQ and Dongtar so much. Now it's time for special research talk. Please welcome Madam Rachel to give a research talk.
Right time now? Can you hear me?
Yes, yes, we hear you.
Okay, thank you very much. Thank you so much for such a nice introduction. I would like to thanks Professor Champ for inviting me to give you this talk. And I would like to tell you that this is not the first time I give a talk for Thailand students, because I met Professor Champ when I was there about 15 years ago. Probably the picture you see on the screen is different than the picture you see now, because it has passed almost 10 years. I really appreciate you having taken this time to listen to my talk. And like, like you was saying in the introduction, I am from University of Évora, although I'm originally Costa Rican. And right now I am in Costa Rica. It's about 11 hours less than in Thailand right now. So it's about 1:30 o'clock for me here in the morning. So I hope this talk will be useful for you, and I will be happy in the future to interact with some of you more. First, I like to know how long time I have, like about an hour or so, I guess. Is that right? Your classroom, an hour and a half.
Maybe
So I
one
okay,
1 hour and a half.
1 hour,
Yes.
1 hour and a half. Okay. So first, I like to give you some motivational background and to tell you why how I am delivering this specific theoretical talk. It's theoretical in a sense, but it's very applied. This about the inverse of moments of discrete random variables. So I will tell you why I am interested in this, and so I will change the screen in later to focus more on the talk. But before that, I would like to give you some background. So, as it was saying, when your colleague give me this nice introduction, I have been very interested in collaborating and studying biological problems. In particular, I'm interested in this topic, which is estimating. Let's see if I can move. Can you see the next page about estimating
Yes, we
animal?
see.
Okay, great. So this I have been interested in this issue of estimating animal abundance, and this part of the talk, I won't show many formulas. It's just the ideas. And when we like to estimate number of animals, we could do a census. That means if you have a small enough area, or if you know that the population is small enough, you can count all the individuals. But the problem is that most of the time, in particular in in wildlife, we need to go to sampling methodologies to count the animals. Usually we choose randomly some areas. We may do a stratification, we may do systematic sampling. All the sampling technique that you may hear before can be used, but within a area, what we like to count is how many animals we see. Like I know in Thailandia, you may have elephants, tigers, or any other wildlife. So this is the issue: how we count them and how we estimate how many are there. So there has been a lot of literature on these issues, books, entire books with many pages, like this one that you are seeing. This is very old book. It's sort of like the Bible, Sievert's book. Sievert is actually a statistician from New Zealand, and he have done a lot of work on linear models and other contributions he have done. But in particular, he wrote this book back in 1982 on the estimation of animal abundance. This is And then more recently, but still old, it's more than 20 years old, this analysis of management of wild population, of animal populations. So then there has been a lot of more books. These are books, no papers, just books on these issues of how do we count animal, how we estimate, what sort of statistical methodologies we use. And more recently, in 2016, this book came out on capture methods for social and medical science, using the same ideas, the same methodologies for estimating evasive and difficult to count human populations. Like sometimes we don't have a easy count of, let's say, illegal immigrants, or there are many other issues in the social science, like for instance, you may want to estimate people with a chronic disease in the medical science, or illegal prostitution in social science, or sometimes census undercount. Say you don't catch everyone in the population at some given time because people moving populations. So in that sense, these methodologies are also very useful. So the issue is that most of the time when you study a population, you are interested in characteristic of those populations. You may want to study the weight of the individuals, or the length, or you like to study habits, and you have certain variables or proportions or parameters that you want to estimate. Well, it happens that when you count animals, the main key parameter that we want to estimate is the number, the N. In human populations, we assume that we know N. It's like if you know the sampling frame where you are sampling, you know how many are there in total, and then you sample from those. But in wildlife, you don't usually know that parameter. So the key parameter of interest is that N, that is an unknown parameter. Of course, we are also interested in other demographic parameters such as survival, recruitment, immigration rates. So these are all parameters that we're interested in, also in wildlife, in animal population. So as you see, we are like being like a demographer of wildlife population. It's sort of like what we do, and we like to study how those populations decrease or increase, or what are the causes of the decreasing, but we need to have an estimate of how many are there. So some of the methodologies that have been used for that, and some of the most common is capture, recapture, and distance sampling. I won't be talking about distance sampling today. I will be talking about capture, recapture. And I'm going to be talking about the basic and simplest estimation methods in capture, recapture. Usually what we try to get is an estimate of P, where P is the probability of capturing individuals, okay? So if we know that probability and we know how many we see, we somehow will get to how many are there. That's the main issue. And we can also combine these two techniques, capture, recapture, and distance sampling. So again, this is motivating the problem, or why I'm interested in the inverse of a random variable. But again, I'm just giving you some context. So biologists, when they do these methodologies, capture method, what they usually do is they take a sample of individuals and they tag them, they mark them. You see, like this duck has a code here on the beak, and then on the nose, and then if they see the duck again, they take the duck, they mark them, and then release the duck, and then when they see that, it's like a recapture. So you can, and that information is being used for estimating how many are there. So when we talk about capture, recapture, there are two large categories, like what we call close populations and we call open population. Closed population is a population where we assume that it doesn't change in time. There is no new individuals, no additions, and no exit of individuals. I mean, we know that most populations are open then, but if you have a window small enough for your captures between capture and recapture, then you could assume that it is closed. So that's an assumption. So that means that if the population is closed is if the number of individuals remain the same during the study period. Then we have open, of course, if there are additions and there are deletions. So if there are new individuals and coming in the population, individuals coming out the populations. So those are the main two classifications. Today, we're going to focus only on the closed population models. In particular, we're going to focus on a two-sample, the simplest one, the two-sample capture model. Just to give you an idea, here is a Venn diagram to the left of this slide. And in that Venn diagram, assume that you don't know the big N that is here. Big N, that is a question mark. But then in the first occasion, you take a sample, let's call it N1. You mark those individuals, N1, you release those individuals, and then in a second sample, you go and take N2 individuals. And you hope that some of the individuals that you take in the second sample has previously been marked. Okay, that's your N11. So if you know this information, N1, N11, and N2, then you can get an estimate of N. So these N10s are individuals that were captured in the first time, but not in the second time. And N01 individuals who were captured in the second time, but not in the first one. Mainly, we are interested in those who were captured in both times. They were captured individuals. In human populations, you may wonder, how can we mark the individuals? Well, we don't mark the individual. We have lists. Let's say you have a list of people in a hospital list, and then you have a list of people who use certain medications in a pharmacy. And then you look which individual from the hospital have gone to the pharmacy. Then you have two lists to estimate how many you may see from that population, taking account the information on the two lists. So this is the two examples. Then if you mark birds, they usually have this on the wings, marks on the legs. And then if you have mammals like deers or wolves, you may tag the ears. And so this is what biology do, and you can tag fish. And then for humans, we need to get some link, some sort of identification so we can link the people from the list. And that sometimes impose some problems of, data protection, but that's an issue I'm not going to discuss here. But anyway, so I'm not talking about anything new. These ideas has been around for a long time. If we go back to demographer like John Grant, he tried to estimate the population of England. And then Pierre-Simon de Laplace tried to estimate the population of France back then, that's many, many years ago. And they didn't have enough registers to think of a census. So they have to use some tricks to estimate the populations. But that idea didn't develop for human populations because of the problem with the assumptions didn't meet. So Peterson was a fisherman and Lincoln was a study of birds in the US, and they brought those ideas to the biology back you know, at the end of the last century and the beginning. So back in the mid last century, there was an explosion of literature and very important contributions from these people like Seaver, Comar, Robson, Duke, Chapman. And this Ken Pollock was my supervisor. He's an Australian, so he's now retired. Jim Nicol is also retired. Some of these people I work with at some point. And then there are some reference human applications in case you like to check. There is a famous quote by this guy here that you know, Einstein, who said, not everything that counts can be counted, and not everything that can be counted counts. And that's especially useful when we think about estimating animal populations, you know. We don't see everything, but we can count them and then we can estimate. Some things that we see are not useful for estimation anyway, but yeah, so I thought to bring you this. So again, if we look at the capture-recapture method, the simplest one is the two sampling computers. And then there are extensions of that we are not going to cover today because of time. And I mean, you know, I can teach one semester of sampling animal population, one entire semester. But then there are more complex situations that have been modeled. And this is when you have more sampling occasions. Here you have the capture time number 1, capture time number 2, 3, 4, 5, and then you may have a way of identifying the individuals. So let's say the first animal was captured the first time, the second time, and it was not seen again in a 5-time period. The second was seen once, the first time and never again. So this is called like a trap shy, or when the animals like the bait, they go again and again, and that's a trap happy. So there is a lot of models that have been used. Other codes that you all know, because very soon we are gonna get into the models, okay? And we know that all models are wrong, but some are useful. That's, you know, some of the things that we hear from George Bock. Other is everything should be as simple as possible, but not simpler. And we will start very simple. We are gonna look at this estimator. This is what is called the Lincoln-Peterson, and if you see intuitively, is very easy to derive, right? Very easy. So, you know, you don't know n, big N, but you know how many you captured the first time, N1. I don't know if I can use, yes, a pointer here, yes. Can you see the pointer? Hello, are you there?
Yes, yes, yes.
Okay, can you see the pointer?
Yes, receive.
Yes? Okay. So you know, you don't know n, big N, but you know that the first time you took N1 individuals. And then you know that in the second time you go and get N2 individuals, and you expect to get some of them that have been marked before. This is the recapture ones. So if you assume, this is a big assumption, but it's reasonable under certain circumstances. If you assume that the proportion of individuals that you mark in the first time that you release them into the overall population, if you make some assumptions, you may think that is the same proportion of individuals that you have been re-encountered in the second sum. So you see, this is a very simple rule of three that we call, right? So if these quantities are known and this is unknown, then we can simply say an estimate of the overall population is just, you know, N1 times 2 divided by N11, right? Very simple, very simple. And then this is this is what we call the Lincoln-Petersen estimate. And this is what most of the time is being used for a two-sample Lincoln-Petersen type. Of course, there's some assumptions here that I'm not getting into, but if you see, the issue here is this N11 could be a random variable, you know, because we don't know how many we are going to re-encounter. And this is, I'm assuming that N1 is fixed and that N2 is fixed because you may have limited resources and you can catch so many. Although you may assume that all of these quantities are random, and then you study this with certain models. So if you see, let's see, let me see, what can I do? Okay, there are applications of this. This is a paper by Ann Chow. This is called the Lincoln-Petersen Science and Station to. So what she tried to estimate based on two incomplete lists was the number of drug users, you know, looking at the overlap in two lists. Now, look, this is very small. So you may think if the recaptures are small, then you have a lot of variation in this estimator. You see? I do this. No, I'm trying. Okay. So there is a problem here if you get N11 equal to 0, right? If you get N11 equal to 0, what happens? Your estimator is undefined. And if you have 0 in the denominator, and if that means that your estimator blow up, I mean, it's like you have a huge population, or maybe because you didn't recapture enough. So that has been studied, the properties of that estimator when you have no recaptures. And Chapman, back in the 1950s, to get around that problem, he just add 1 to each quantity in the numerator and the denominator, and then to get around this indefinition, because this Chapman estimator is no longer undefined. So he used some hypergeometric distributions to study the properties of this estimator. And he found that this estimator is less biased than the than the Lincoln-Petersen original estimator. And then there has been many other estimators proposed. Bailey's proposed this estimator. Chow proposed this estimator who also have that problem. You also could think of a problem like this. You have, let's say, first capture, second capture, or one list A and one list B. And what happened is that you don't know this N00. You know all these quantities, but you don't know how many you didn't see. And you need to estimate that N. So that's another way of looking at the problem. You know, so again, we have the Venn diagram, etc. So I'm going to switch now because now I'm going to tell you why I have been interested in, well, now you know what the problem is. Let me see if I can interrupt this sharing. Now you know what the problem is. The problem is that you have estimator that could be indefined, and you can get around that, some mathematical tricks. But the issue is that if you want to study the properties of this estimator, this has been done in the past, what happens is you have one random variable in the denominator that could be 1, 2, 3, 4. We don't want it to be 0 because the estimator is undefined. So what we're interested is to estimate the inverse, to see what happened with that random variable, which is the inverse of an integer, non-zero integer, right? So we have all this theory, and it seems weird, why this haven't been studied enough. I mean, we know that, to get around, I didn't show you that, but to get around a variance of the estimator, when we look at an estimator, we want to study two important things, the variance and the bias. But for the bias, you need to know the truth, and we often don't know the truth. Okay, but we can use some models, and we can do some simulations to get around that. So let me see. I don't know how we are doing with time, but I think we have plenty of time. And I don't want to tire you too much with this issue, but let me share with you this. This is a little bit more formal, this other part of the talk, because the first part was the motivation. And now, let me see where that is. No, let me see. Well, let me show you a little bit here of this, because this is going to be useful for later. We can, the simplest model is a binomial. If you do this in a binomial model, n1 over n, let me see if I can get the pointer again. N1 over n is the probability of capturing in the first time, individuals in the first time. And this is the probability of not capturing. So if we consider n1, 1, a random variable with n1 and n fixed, we can write this model here, assuming that the probability of capturing the first time is n1 over n. So we know that the expected value of n11 is basically p times n2. And if we put p times n2, we can easily obtain our Lincoln-Petersen estimate. I mean, I don't know if you see that, but let me see if I can write it here. Let's see, so that you can see what I'm talking about. Okay, the expected value of n1 1 is equal to n2 times p1. P1 being the probability of capturing the first time. So that means that this is equal to n2 n1 divided by n. So you see, if we take this n, big N is equal to n1 n2 divided by the expected value of n11. Okay, so if we don't know this expected value, but we observe n11, then we get an estimate. Okay, so that's the Lincoln-Petersen estimate. n1 n2 divided by n11. Okay, and we can get this with other models also. Let's see how we can get this again. Okay, so we can do that for several models. Ahora, how can I move the? Are you seeing what I'm showing? Yeah. Let me see if I can clear. Okay.
We can see.
So we can do. We can see the same with the hypergeometric, or with another other models like these are count models, right? Let me see if I cannot. Okay, with a multinomial, and then we can, we are looking at the properties, and we can derive, if we know the properties, if we know the distribution of n11, we can derive the variance using the delta method. Okay, we have to do some math there, but we can do that. again, and we are interested in the properties. So let me now see if I can, okay, do this. Okay, now I'm gonna get a little bit more formal. Let me see. How do I share again? Okay, here. Let me see. And we are sort of like summarize what I have said before. It seems repetitive, but now I'm gonna go faster. So we got some context. Now we are gonna look at positive zero truncated discrete distributions and look at what happened to the behavior of the inverse of those zero truncated distributions. Okay, so the context again, well, we already say it: demographic parameters, wildlife, capture recapture, and sorry because here I changed notation, okay, but just bear with me, and the idea is the same, you know. Now we have I'm calling the Lincoln Peterson, and I'm calling, sorry for that change, but I am saying that the recapture ones is this random variable k, and that big K is the number taken from the first sample, and n is the number taken in the second sample. Okay, and basically what we have is this estimator in the domain of the positive integers. We are not going to include zero. Okay, that's equation one, is the Lincoln-Peterson estimator. And now let me see if I can move ahead. No. Okay, so let me see. Okay, I know. I'm gonna put it this way now, I think. Okay, so more context we already say. This has been a study, and Chapman proposed that modification, which was just a mathematical trick. Now, we don't need that trick if we restrict to probability mass functions, right, that do not count zero. That means like the truncated, like the zero truncated, like, you know, there are several well-studied distributions like the zero truncated binomial and zero truncated Poisson, that those probability mass functions are well known, and they have been implemented in the ARC project under the libraries of BigAm and extra distributions. We can also easily, if we know the distribution, we can also just do manual implementation, conditioning on non-zero. If we have a known probability mass function, including zero, we can just condition on non-zero values and transform the probability mass function divided by 1 minus the probability of observing zero. We know that trick already. I mean, we might have seen that trick. So look at what happened to the inverse of non-zero positive values or positive integers. So again, if we have a non-negative integer value, you know, meaning that non-negative will include zero, right? But the probability mass function of px equal k actually is gonna be the same as the probability mass function of the inverse, because, you know, this y 1 over x, if x is an integer, then the probability is the same, because this is a how you call it, one-to-one transformation. Now, if we if we have to deal with the problem of zero, we know that we can condition, so no problem. But what is going to be the support of this transform variable? You know, we have the support of y, let's say, is 1, 2, 3. So the support of x, sorry, 1, 2, 3, the support of y will be 1, 1 over 2, 1 over 3, and it is going to clump to 0, you know, as we go to infinity. So this is a countable set of positive real number that will accumulate at 0, because this is a monotonic transformation that we have. So very, very simple. So is a non-integer anymore. Why? Why is not integer? You know, it's a real number, but it's discrete at some point, you know. I mean, you know, you have 1 and then you jump from 1 to 1.5 and then to 1/3, etc., etc. So although the probability of observing k, let's say, is exactly the same as observing 1 over k, because that monotonic transformation. So what we are interested in is to see what happened to the inverse moments, like the expected values of 1 over x, you know, and this come up in many applications, not only in wildlife and you know, and counting animals or evasive population. This expectation of the inverse of a number come in risk analysis, queen theory, harmonic means, etc., in their different circumstances. So, you know, we have the expectation of the distribution of x, of y. So what happened is that this expectation may converge or may not converge. What depends on the decay of p, of that probability, how fast it goes. You know, if you have x is a geometric distribution, then the expectation is finite, you know, and you can compute higher moments of that expectation. You can compute variances. So in summary, you have these things. You have a countable subset, you know, between 0 and 1 is a countable subset, because you have 1, 1/2, 1/3, and it comes to 0, you know, for k positive. So it's a discrete type distribution or non-integer value. And then you have a probability mass function that inherited from the original random variable by re-indexing. So the probabilities are going to be the same. The probability of observing k is the same as observing 1 over k. The expectation will depend on the decay of k, and there is some pathology that we already talked about. So let's observe, you know, a few examples that what happened. So if x is uniform between 0 and n, then it happened that you can get this expectation, which hn is the harmonic. These are the n harmonic and the second harmonic numbers. So you get very interesting stuff here. And for large n, you know, you can approximate those numbers. So you may not get closed forms, but you can do approximations. And look at what happened to different discrete uniforms. So if you have the discrete uniforms in the top row for different values of n equal 10, n equal 50, n equal 100. Look what happened if you look at the inverse, at the probability of the inverse. So you see how here there is accumulation. Let me see if I can do this. But, you know, very interesting here. So that they clump to 0 here, those, but then the behavior does, I mean, you change the shape and the behavior, but the probabilities are the same. Let me see if I can show you other examples here. Well, if you can do this, then you can compute again the expectations, let's say if you have a geometric distribution, because it converges, you can get these exact expectations and variance forms. But look at what happened to the plots when you look at the plot. So this on the top is X, and then on the bottom is the inverse. And you can see how they jump, they jump from one to 1/2 to 1/3, etc. And then when you change the parameters, this is for p equal 0.2, from p equal 0.5, and so you increase p, this is what happened. And then you can, where is it? Sorry. You can look at the variance as a function of p and the expected values as a function of p, and you can study those behavior of those distribution. If you have a binomial, let's say this is a zero truncated binomial, again, for certain value of n's, you can do approximations. You have to do some math to get to those approximations. There is no closed forms. Okay, this is what happened on the top for different values of p. I think it's for the same n here. So when you change p, this is what happened. And you can see the inverse. You see, curiously, because most of the time you don't have closed form, you only have approximations to the expectations. Okay, and let's see. This is what happened to a truncated Poisson distribution. Again, on the top you have x, and on the bottom you have the inverse of x. And then you could have the hypergeometric distribution. Here it's more difficult to get closed forms, but if you make some assumptions, and for large n's, you can do some approximations, and then you know that everything. I mean, if because of the large numbers, you can approximate to normals also. So here is what they look for, and then what I did here is some small simulations study to compare, let's say for the hypergeometric distribution for these parameters. I did some simulation study to see how the expectations and the variance compare for particular cases. No? But again, you don't have closed forms here. So summarizing, because the talk is getting long, and we want to get feedback from you, and if you have questions, we can do exact computations for small populations. If we have large populations, then we can do binomials approximations and normal approximations. And one interesting thing that is the tail probabilities, how they fall, because then we can do extreme value theorems to study some of the behaviors of this distribution. So some final remarks. So basically, what we have been doing is to characterize the inverse moments on some discrete random variables. And for some of them, we have exact expression, but some useful approximations also are possible. These results are applicable in many analytical and modeling contexts where inverse transformations are relevant, and for rare events, when inverse probability is very often using weightings for sampling. So there are some theoretical consideration also for number theory. So if you are interested in these issues, one situation is that you can use some interesting math associated to this, like number theory, infinitesimal calculus, approximations of continuous to discrete random variables. All of the things are in place, and even Bayesian stuff also, because a lot of the time we use In Bayesian theory, we use the inverse of random variables. So here you have some references, and many thanks for listening to this talk. I know it's simple stuff, no very complex stuff, because the simple concept could bring nice, interesting mathematics. So now I'm gonna interrupt, and I will be happy to hear questions, comments. If you thought anything interesting, the main thing is interesting for me is that simple could get complicated, right? But not too complicated. I don't know your background, so I know that many of you are more statisticians or mathematicians and may not be interested in counting. But here we have some math and stat involved. So yeah, I'm open to questions and comments, please.
Okay, please clap your hand to Ajahn Russell.
Thank you.
Okay, this time, in data science, so we have the specific to the minor. Let's choose to minor statistics, minor computer science, and minor mathematics. So, can you suggest the course that, so if he or she want to choose your research, maybe your research, what is the basic course or the background? Okay.
Yeah. You are in a very interesting field right now, and many exciting things in data science and big data and stuff. If you look at this, you say, well, this is a little bit of theory, things that we learn in probability, etc., etc. And in my field, sometimes we don't have big data, and we have a small data, and the issue is that sometimes we don't even have recaptures. What happens if we don't get a recapture? Although with new technologies, you can tag an animal and put a radio, and you can follow the animals all throughout their lifespan. Let's say you catch a whale or you catch an elephant, and you can put a radio or a tag, and you can insert it, and then you can make measurements of these individuals like we do with humans. So a lot of that information that you collect, and that's big data for one individual. So sort of like the paradigm here is, now we are not interested in computing population. We are interested in computing, making inference from one individual based on all the information about that individual, or a group, or it could be a small group of individuals. So let's say if you have radio telemetry, and then you put that radio and you see how the movements of the individuals and the activities, if they are moving fast, or they are hunting, or if they are resting, and then you can get a lot of that information with, and you can analyze the patterns of what happened with these individuals. So you do have so it's like we are in a change of paradigm based on population modeling and estimating numbers, and then you have looking at what happened to each of them it could be a small sample, but you have a lot of data about them. So that's one thing that the problem is that sometimes we forget the basic. I mean, we are more interested now in algorithms, and data mining, and patterns, but sometimes we forget the basics and why, all this work and what is it that make it work. So we cannot forget the basic, what is behind that. So that's important for data science. Now we know that because we can do many things with artificial intelligence also, but many times we don't know what is going on there behind the algorithm, and we need to think harder about what is going on to be able to make some contributions. There is these are like trends. Like there was a time where many people want Bayesian state. Everyone wants to be Bayesian because that was, now we can. Bayesian is all about getting expectations with, like getting an expectation is a sum if we have a discrete variable, but it's an integral if we have a continuous variable. And the issue is that sometimes we have complex integrals that have not closed forms. So what we do is do Monte Carlo, repeat an experiment many, many times to get to the means. And Bayesian stuff have a lot to do with this sort of simulation, and then you use algorithm, they give something and stuff like that. And this is changing the paradigm, but we cannot forget the basics. That's the main message. We have to think about why this work. Like I start talking to you about biology, and this is another thing you are, a statistician or a mathematician or a computer scientist. These are all techniques, methodology. I mean, you can be a good data scientist, but you need to know substantial field where you apply that, because otherwise you just become a technician, and you can do research, you can do simulation, but it's important to think about applications. Where do you want to apply what you have learned with these methodologies? And what sort of contributions can you make to the scientific literature? I didn't tell you about this, but let's say just another example, because these ideas of capture not only apply to animals, and I already talked about health science, like measuring the stuff from individuals. But there is an interesting thing of application of capture that has to do with estimating the number of bugs in a program. How many, a bug, like errors. When you write a computer program, it may be subject to errors. So if you run the program, you may, one student may find some error, or a student may find another error. So how many errors in a computer program there may be, or in a type of text, or in an algorithm, or now that we're thinking about data science or big data, how many errors there are in web pages. So these methodologies, capture can be used to estimate those errors. How many? So many applications. But yes, it's important that you think about a specific field of study where you can apply the methodologies. It's fundamental, I think, so you don't become just a technician. Sorry, I talk too much, but I want to hear my question. I don't know if that sort of answered your question, Professor Cham.
So yes,
Was that
definitely. It's
useful?
linked to that you talk. So maybe last question. So if we have the basic call to biology, right? So it will support for this method, right?
I am hearing with the echo. So
Just
Okay. So is it okay?
Yes, better. Yes.
Okay. So we know the background for the biology. So it will support to recapture, right? I think. So another case, so if we apply to maybe most of students, so next time we go to the deal project with the industrial or something like that. So I will suggest them to observe the zero ton case. So because most of them know the classification, right? And the zero ton case, this is an idea, I think. So this is a good thing that I will talk to them later.
Yes, for
Okay.
sure. You know, it's funny because Chapman and many other mathematicians, these theoretical statisticians, were getting around how to come up with estimators that are not undefined, so that we don't have problems with computing. Like having infinite expected values and things like that. So they were tricking the formula, but these are mathematical convenience. You can just truncate and get the probabilities of everything, and do all the and I haven't seen this discussed. It's funny because you say, why something as simple as thinking about the inverse of these distributions? You don't have, you in Bayesian theory, you do have a lot of like inverse gamma, inverse normal, inverse stuff. But the discrete is not, it has not been studied as well as the continuous cases. And maybe this is because of the type of applications, but counts are used in many queuing theory, like I say, like industry, in many things has been used. But for some reason, if you go look at the literature, you know because mathematically may become hard to do those approximations in some cases. But yeah, you have applications in many contexts, many contexts, and I urge you to, when you are young students, you are probably, many of you have working experience, but if you are interested in applications and research, even if you work for a company, maybe you don't want to do like scientists, but think of a particular context, like, and go across disciplines. Sometimes things that are useful in one discipline may be very useful in other disciplines. So for many years, capture recapture was used for animals, even though the original idea was tried to apply to human populations, like studying the population of France in the 1700s, and the 16 the populations of but then it didn't work, so it was used for animals. But most recently, in epidemiology, a lot of application of capture capture. If you look capture capture epidemiology or capture capture industry or computer software, you will see a lot of application. But this is just capture capture, very specific methodology. You can think of many other, like estimating the number of taxi cabs in Bangkok, or in estimating the number of homeless, or so many applications of this. But this is about what this related to this talk. There are many other things that you may look at. You have to choose things. You have to have a critical thinking. That's fundamental. So these are third-year students.
Yes.
And they have how many years more to graduate?
How many
How
years?
many more? How many years program?
Maybe 4.
4.
Yes.
And then what happened after? You go to work at the industry, or you work master's, PhD? What do you do?
So for my students,
Yes, these students here.
just a moment. Okay, maybe next time, maybe they will go to training with the industrial, maybe or the company. After they will study about the 1 semester, and after they finish,
Okay.
okay, they go to find the first job now. But
Okay.
this time, the
Okay.
course that most of them choose the minor of computer science, minor of statistics for the second. And for this time, this course is a cover to analyze about the data, and they will select it to construct the model and analyze something with the operation or industrial, something like that, to do the project
They
before
have to do thesis or
Exactly.
project. They have to do. Okay. Okay. I didn't talk too much about the University of Evora, but at the University of Evora, we also have a master's programs in statistical modeling and data science also. And we have PhD program in mathematics with different emphasis. And sometimes students can do their own program if they want to study here. In fact, the first time I went to Thailand, I was in Vietnam with uh, Erasmus Erasmus fellowship. So I was 2 months there. But sometimes you can get also fellowships for many Asian students came to Evora sometimes, to especially South Asia. So we have even Philippines, Vietnamese, um, we have Bangladesh, Indians, many. So if you are ever interested in looking for fellowships or things like that, just give a peek to the university. It's not a, let's say, many times students from overseas look at the United States. Like I was from Costa Rica, I went to study to the United States. I don't want to go there right now, but sometimes, students look for United States. But you have also in Europe many different programs, and you have good universities in certain areas. So if you are interested in finding out about that, just take a look at the international grants and programs. So you may have possibility of going out to study, and that's an important thing to do for students, so that you can open up other horizons, and see other things. Or even if you work, certain companies hire like international students also. So nowadays we can do a lot of things virtually.
Okay.
So yeah.
So that's it.
I don't know if any student have a question or they want to make a comment. I don't know how their English is at this point. You can ask questions or anything I can
Most of them are shy.
try.
Because you is the first professor that they are meet you for
Oh,
maybe I think you are the first professor, because they study with me 3 courses, and this is the third course, and you are the first professor that meet undergraduate student now, I think. Okay, so okay, Kim, next.
Okay, thank you very much, Ajahn Rachel, for sharing your research with us today. Now is a good moment, so let us turn our camera and take a good photo together.
Good photo.
oh, thank you.
Okay, we can move. and let's look back to me and we will take a photo with Ajahn Russell
My,
ไปอยู่ข้างหน้า
with
หน่อย
my camera.
Okay, just a moment.
Okay,
คอยเอา
let me see.
ไม่ต้องยืน
Okay.
ที่สองก็หันมาทางนี้เดินส่วนนี้ไปยืนเร็ว
อยู่นี่ใช่ไหม
หันไปหน่อย
ๆเร็วๆข้างหลังอ้อมไปที่โน้นอ่ะไอ้ปื้มเร็ว
หันไปนู่น
ๆเร็ว
อาจารย์หันไปหาอาจารย์ไปหัน
Just tell me when you are ready so I can take the picture.
โอเค
ๆ Okay, just a moment.
Oh, you're turning around. Okay.
ยาว
อันนี้ก็หันไปโอเคหันมาทางนี้ก่อนโอเค โอเค one two three smile so I will selfie now
อาจารย์เสียวจัง
เดี๋ยวฟูกิมาถ่ายโอเคทำไมหน้ารูปว่าเป็นลมแล้ว one two three เอาฟูกิมาถ่าย again ฟูกิโอเค3 2one two three วิดีโอไหนได้โอเค we will take a video and say thank you to Professor Russell now okay 1 2 3 thank you
How many are you there?
I think around 45 maybe
45. Wow.